The first thing we're going to do is definitions of energy. All right, the first one we've got here is chemical reactions are going to transfer energy. Now, we've talked about them with respect to reactants products moving around, but a lot of the time there will be an energy transformation that you can feel. Now, remember, energy by definition is the capacity to do work. And so we're going to work it with respect to breaking and forming bonds. So kinetic energy is the energy of motion. So anything that's moving will have kinetic energy. That's mechanical, thermal, electrical, etc. Okay, potential energy is the energy of position. And this is gravitational, electrostatic, chemical. So if you're standing on top of a 6-foot table, then you have potential energy because of your position. If you're standing on the floor, you have less potential energy. But you still have potential energy unless you're moving. As you move from high to low or low to high, then that your energy of motion, so that's kinetic. So chemical energy then is the energy of reaction. It's going to be the potential within the bonds, and you're going to break bonds and reform them, etc. Okay, thermal energy is the energy of random motion of particles. So particles moving, and this is, you use this all the time. We call this temperature. And radiant energy I just throw in because it's the energy of the sun. It's radiating energy, so I just like to throw it in for fun and entertainment. Now we'll talk about kinetic energy, potential energy, but mostly chemical energy because it's a form of potential energy. Okay, so if we talk about chemical energy, what we're talking about is work, and work, remember, is force times distance. And if you've taken physics, or if you're taking physics, this will sound awful familiar because it works accordingly. So when we talk about electrostatic potential energy, electrostatic has to do with charges. So we're talking about in a chemical bond, especially if it's ionic salts, etc. You have your cation and your anion. They act like magnets. So you're going to have attraction between opposite charged particles, and you're going to have repulsion between the same charged particles. And we also have to include the distance between charges. So think of magnets. Post said I shouldn't have done that. Okay, think about magnets, and it's really critical if you're holding two magnets, and they can be repelling or attracting, that doesn't matter. But if you hold them far apart, there's no interaction. It's only as you get them closer together that they're either going to snap together because they attract, or they're going to start repelling. It's kind of fun to play with two magnets that have both north poles and see how far you can get them to each other, and they're constantly repelling. Well, this is exactly what charges do, because charges are really nothing more than magnets. So if we need to visualize this, we have the attraction again between opposite charges, repulsion between the same charges, and then distance between. So we went through that before, so what's going on? Well, if you notice that as you have opposite charges together, when they come together, the energy drops. Whereas if you put two charges that are similar, the energy increases as you get them closer and closer together. So this actually makes sense because, again, we've got the separation. They're infinitely far apart. And then as you bring them closer, you see this. So distance has a huge effect in this because as you get them farther out, there's no attraction or repulsion. Okay? So again, we've still got the attraction between opposite and repulsion between the same, and we're still looking at distance. So how does this work? Well, as particles in a salt, remember this is an ionic compound, come together in an array and pack. The packing is a function of the size, distance between the particles, and the charges. So as they as they pack closer together, then you have a decrease in the energy. So the best packing is the setup where the energy that's achieved is the lowest for ionic compounds. Okay, so that takes us to the first law of thermodynamics, which is the conservation of energy. Energy can not be created or destroyed. It can only be converted. Okay, which is why when they that's an R, verted. Okay, so that's why when they talk about renewable energy, I, I, I think it's funny because to me it's not renewable because renewable assumes that you're creating it again. It's recycled energy, but recycled doesn't sound as cool. So you don't talk about recycled energy, you're talking about renewable energy, but it is recycled energy because you can't make energy. So the total energy of the universe is constant. Okay, so the total energy is equal to energy of the system is equal to the energy of the surroundings is equal to zero. So this is system. This is surroundings. That's what the surroundings. This is what the SYS and the SYE. So the bottom line is since the change in energy total has got to equal the change of the two species and it has to equal to zero, then what that means is that the energy of the system has to be the opposite of that of the surroundings. Okay. This is this is simple because you're just transferring the energy. You either give it off or you get it. And if you get it, you got it from somewhere. And if you give it, something has to take it. And so we're going to talk about these things as our system and our surroundings. So the first thing is what's a system and what's a surroundings? So a system is the sample or portion under study. And the surroundings is everything else. So, wait, what's that mean? What it means is you're going to transfer energy from the system to the surroundings and back. Notice it's an equilibrium because we're going back and forth. So, systems are open, closed, or isolated. Okay, so this would be an open system. Why is this one an open system? Because it's open to the air. And so, therefore, we can call it open. It can be totally closed, in which case we have our system separated from our surroundings and they're set. Or it can be isolated. Now, calorimetry in lab, we're going to isolate it. How do you isolate something? An easy way is to use styrofoam. Styrofoam does not transfer energy. It's cooler, keeps cold things cold or hot things cold or hot things hot. That was ridiculous. And always the joke is how does it know? Well, bottom line is it's not that it knows. It just isolates whatever's in the thermos or the cooler from everything else. So if it was cold, it's going to stay cold. If it's hot, it's going to stay hot. So, and remember, heat always flows from high to low, which is why if you keep it isolated in some sort of thermos or whatever, cold will stay cold longer than hot will stay hot because the hot is trying to escape, whereas the cold is like trying to avoid catching heat. It's not giving anything up. So, what we're talking about is energy changes. So the change of energy is equal to Q plus W. Well, Q is the heat transferred, whereas W is the work done. So Q is heat. And you're going to see this a lot. So just remember, if you see Q, that's heat or temperature. And work is work. So what are we doing here? Well, if energy is entering a system, it carries a positive sign. So if heat is absorbed by the system, then Q is greater than 0. If work is done on a system, then work is greater than 0. So if it's entering a system, that means that the system is absorbing the heat or it's having the work done on it. Okay? Whereas if it's leaving a system, it carries a negative sign. So if heat is emitted by the system, then Q is less than 0. If work is done by the system, then work is less than 0. So what it really boils down to, if the heat is coming in, it's positive. If work is coming in, it's positive. If heat is going out, it is negative. And if work is going out, it's negative. So that's really what you have to remember is the question is work being done on or by the system? So let's work a problem. Okay, a gas does 207 whatever of work while expanding and emits that much heat. What is delta E? Well, delta E is equal to Q plus W. All right, so it does so much work. So work, since the gas is the system and it's doing the work, it's giving off the energy. So it's giving off 207.4 joules. Okay, it says it's emitting the heat. So it's 0.536 kilojoules of heat. So when we go to add them together, we'll end up with negative 2, I forgot the sign. Signs are important. Now remember, the sign is critical because it gives you the directionality. Okay? Because it's emitting the heat. So, can I add them together and get negative 217.936? No. Our units must be the same. So, either work, the joules has to go to kilojoules, or the kilojoules have to go to joules. Does it matter? Not unless it specifies. So, if we're doing this in D2L on the quiz, and you will, I will specify what delta E is. Or if it's a multiple choice, I might not specify, and you have to figure out which one it is. But bottom line is they both have to be converted. Now, does it matter? No. So I'm going to take the easy way, and I'm going to convert them to joules. So work is negative 217.4 joules, and Q is negative 536 joules. that means that delta E is negative 753.4 joules. But if we're looking at significant figures, we have the least number of decimals because we're adding and subtracting. So we would report it as a negative 753 joules. If we were on kilojoules, it'd be negative 53 kilojoules. Does it matter which one we pick? No, as long as it's not specified. In D2L, it will be specified. Because if y'all, as y'all have figured out, D2L is not friendly with weird numbers. Okay, so a gas absorbs that much heat so the Q is going to be positive 315.7 joules while being compressed, but it's doing 225 kilojoules of work. Okay, so again, it doesn't matter whether I leave this in joules or kilojoules, but I have to convert it one way or another because they have to add. So in this particular case, I'll go ahead and convert that delta E is going to be equal to positive 3157 kilojoules plus a negative 0.225 kilojoules. So that's going to give us a whopping 0.907 kilojoules. But when we go to add it together, we have three significant figures. So we would report it in three significant figures. Why does that not look right? Oh, and it's going to be positive. So we'll have this many kilojoules as we go. Okay? So the bottom line is do we have to put the positive in? Yes. No. Okay. If you don't put it in, it's understood to be positive. However, you might want to get in the habit of putting the positives in here only so that you remember that when it's negative, that you're going to have to account for that as well. Okay? So, again, it's just a good idea. So what we've done in this section is we have started with the definitions and we've shown you how heat and work combine to give you delta E. In the next section, we will continue on with equations.